So, welcome back. What we did before the tea was to look at two categories of optimizations. One was to uh, do classical optimizations to eliminate redundant computations. The second was to optimize heap memory usage by nullifying heap memory that is not going to be used. Okay, so now what we want to do is, based on these two classes of optimizations, we want to make some general assumptions. So we want to take a 20,000 feet view of what program analysis is, and then we'll once again come down to ground and talk about specific program analyses. So we're trying to answer this question: what is program analysis? Because we've seen the examples of applications of program analysis. So what are the characteristics that this technique called program analysis should have in order to serve applications, diverse applications such as this? Okay, so let's step back a bit. When we talk about software development, the three fundamental requirements of software are correctness, robustness, and performance. There are many other requirements. For example, compliance to legal rules, security, privacy, maintainability, interoperability, usability. All these are desired features of software, but the three primary requirements, the overarching requirements, the most important requirements are: software must be correct, software must perform efficiently, and software must be robust. You know, in case of wrong inputs, in case of exceptions, software must have a graceful way of handling them. Software should not be fragile. You try to do something and just breaks, right? So these are the three primary requirements. So and how are these requirements met? Well, a programmer is supposed to handle these. A programmer is supposed to identify these. So what are the programmer's tasks? A programmer is supposed to understand the program. A programmer is supposed to reason about the program. A programmer is supposed to explain the program to the programmer and to other programmers, right? And programmer is supposed to be able to debug programs and modify programs. So there are certain requirements, and these requirements are met by a programmer doing the following tasks. Okay, program analysis deals with the first of these three. Program analysis helps a programmer in understanding the program, in reasoning about the program, and in explaining the program. Program analysis is a set of techniques that helps programmers discover useful information out of programs. And the main theme of program analysis is, and each and every word here is very important, to build suitable abstractions for safe and precise modeling of runtime behavior of programs efficiently. First thing is, a program analysis builds suitable abstractions. Okay, program analysis cannot tell everything about a program, but it can tell us at an abstract level. For example, we looked at the application of heap memory. Program analysis can say, here I am not accessing LPTR out of X. No statement below this is going to access LPTR out of X. That's an abstraction of the runtime behavior of a program. So uh, can we tell them not to talk, please, at the back? Please don't talk. Disturbs me. So we have to create abstractions of runtime memory, and these abstractions have to be suitable. Suitable in the sense that it should be possible, they should answer the question that we are asking. Okay, so we have to build suitable abstractions of runtime behavior, and these abstractions should model runtime behavior precisely and safely. Safely as in they should not give a wrong answer to any question that may create a create a harmful error. We will see soon what we mean by that. And they should answer the question as precisely as possible. Obviously static analysis is undecidable, so exact answers cannot be given, but so there would be some spurious answers, but the spuriousness should be as small as possible, and the whole thing should be done efficiently. And the other thing that I did not say was, when I say building these abstractions are, once we build these abstractions, we should be able to write programs for them. They should not, they should be systematic abstractions. Okay, so what we have is, we have a static world and we have a dynamic world. In a static world we have a program code. In a dynamic world we have processes corresponding to a program. This is a program in execution. So the characteristics of the two correspond to each other, but the characteristics of the two differ a lot. How do they differ? The static world, in the static world, program code is abstract. Why is it abstract? Because I don't know what is the value in the variable. At runtime I would know what is the value of variable x. At compile time I do not know. In the static world I do not know. So it is abstract. There is a single instance of the program code, and the program code is bounded. You can't have an infinitely long program, right? It's abstract, it's bounded, and there is a single instance of this. On the other hand, in the dynamic world, the corresponding process is concrete because we know the values of variables. The corresponding process is unbounded because we don't know whether it will terminate or not. And there are infinitely many possibilities of this. So we have to map these two, right? And now each of these processes may create a memory which has similar properties. It's concrete, unbounded, and infinitely many. And what we want is, we want summary information of what happens to the data when the program executes. And we want that information in the static world, in the not dynamic world. We are not talking about dynamic analysis, we are talking about static analysis. What program analysis does is essentially bypasses going through this and says, okay, I have a program code, I can look at the program code and can give you summary information which has these properties. That is safe and precise modeling of that, suitable abstractions for safe and precise modeling of runtime behavior of the program, and these abstractions are obtained efficiently and in a systematic way. So that is the theme of program analysis. So what are the desired features of, before I go any further, I would like to pause here and take any questions. Anyone has a question? Okay, so let's proceed. So what are the characteristic features of program analysis? So first of all, program analysis should be automatic, right? We don't want manual intervention. It should work, a compiler or a tool should automatically figure out. Okay, it could be static or dynamic. It should be possible for us to build abstractions without executing the programs or along with program execution. In most cases, people focus on static program analysis, but a lot of dynamic program analysis is also done. And as I said yesterday, we can combine static and dynamic analysis as well. Program analysis should be sound, must cover all execution instances. It shouldn't happen that program analysis gives me some conclusion, but that conclusion doesn't cover a particular execution instance. There could be infinitely many execution instances, and yet it should cover everything. A case in point is what we saw just now before the tea break. We're talking about optimizing heap memory. When we build the abstraction, I'm using RPTR out of X or LPTR out of X, it's instantly clear that it will cover all programs, all executions, all execution instances. Doesn't matter where X points to, doesn't matter how many times while loop is executed, right? So we have to cover, or if we leave out certain execution instances, then that is an unsound analysis. Okay? There's this term called soundy which people have proposed, but let's leave that aside. Soundy is sound modulo certain well-known assumptions about difficult to analyze features of programs. But let's not talk about that. The other feature is program analysis should be precise, must give accurate result for every execution instance. This can only be approximated. This cannot actually be reached because program analysis is undecidable, right? Program analysis must be efficient. Uh, it should consume resources uh, economically as possible. Okay. Program analysis should scale, should work for large programs, should work for only small programs. So these are the desired characteristics, these are desired features in program analysis. Not every feature is available exactly as we want in every program analysis, but this is what we should aim for when we try to design program analysis. Okay. So why is it useful? It is useful for code optimization. We may want to improve time, space, energy or power efficiency. You have a software running on a mobile phone, you don't want it to consume too much of a battery. Does anyone have an idea of what kind of things one can do for energy and power optimization? Just a guess. What can we do? How? I mean, exactly what? Exactly what can be done or should be done? Yeah, give the mic to me. Yeah.
Something we saw like strength reduction.
Okay. Anything else? So turns out that the maximum memory consumption happens in memory. Maximum energy consumption happens in memory. So one way in which we can optimize for energy and power is to minimize the bit flips within the memory. So if we can identify computations happening in the memory, and there are some details we can find out, do what is called bit width analysis and try to somehow arrange the computation so that 0 becoming 1, 1 becoming 0, that is minimized, that will reduce the memory consumption. So there are several analyses that can address things like these, right? Then there is verification and validation. We would like to talk about, does the program do what it is intending to be doing? That's one application of program analysis, and we have some examples. And then there are software engineering. I may want to maintain a software, I may want to detect bugs, I may want to fix bugs, I may want to enhance the software, I may want to migrate the software from one platform to the other. And then there are interactive development environments, IDE, where I want to navigate between definitions and uses of variables. I may want to do intelligent auto completion. So VS Code gives you auto completion. If I type something, it tells you, what are the possible classes or what are the possible variables, but does it do it intelligently? Can we figure out what is there in the scope at the point? Maybe at the moment VS Code doesn't do it, but it's possible for us to do it, right? So this is one of the applications of the COS SSA that we are trying to build. It should be possible for a user to navigate through the program through an IDE more precisely based on definitions which are in some other files, in some other functions, etc. Okay. So some examples of verification and validation. So a program analysis should be able to flag use of uninitialized variables, null pointer dereference, use after free, double free, dead code, unreachable code, resource leak. Resource leak, again, you have allocated memory and are not going to use it, so memory leaks away. Or you have allocated a file descriptor and you're not going to use it, so your file descriptor table may become full at some point of time. You may not be able to open a new file. You may create sockets and not use them. You may run out of socket connections. Locks, threads, server connections, these are all resources. So this general theory, general concept called resource leak checking. Analysis aimed at checking leaks of resources. Then there are compute exceptions such as divide by zero, integer, floating point. Then there are borrow checking violation in Rust, for example. If if a data structure is pointed to by one variable, and that's a pointer, and it's marked as mutable, then other pointer cannot point to it, other pointer can maybe read it but not write to it. So these are called borrow checker violations. Then there is taint propagation. So I'm collecting maybe name or email address of a user, and or maybe there is, or possibly maybe there is a overflow injection attack that can happen. So the input data that I'm getting here could be tainted, and where does it flow? Does it flow to a sensitive part in the program? That's taint propagation. And there's buffer overflow. So I have created a buffer of maybe 50 locations, and am I writing 51 locations? Am I writing a data of 55 locations? Why could this be a problem? Why could buffer overflow be a problem? Any guesses? Let's say I have allocated space for this in the program, and at runtime it writes more. I have 50 locations, and at runtime I send a string that has 52 locations. Why could that be a problem? Okay. Uh, so the remark, repeat that. Yeah.
Sir, another program might be using that memory, so if it is overwritten, it might get corrupted.
Yes, but it's all within, I'm just talking about just two locations. So what could happen?
Accessing a portion that is not supposed to be accessed.
That's a general statement. Yes, can you make it more specific? So what she's saying is you are accessing a location that you're not supposed to access. That's a general statement. Can we make it more precise?
Say that part of the memory could be accessed only by, like, in a privileged mode, and you are running in an unprivileged mode. Suppose you're touching a kernel code, you can actually corrupt the kernel itself and
Yeah, but
gain
I'm
access.
not talking about arbitrary locations. I'm saying instead of 50, you're writing 52. A very simple example is you create a stack frame, you create an activation record, you have locations assigned, and below that is your return address from where the call was made. So if you write some extra locations, you may be able to transfer control to some other procedure which the user has indicated, and that's how several attacks have happened. That is how people gain control of your program, by overwriting return address. So the control returns to some location, not the location where you intended, but the location where the attacker wanted to reach. Okay, so just by writing some extra locations, you are corrupting that, and you are carefully manipulating it in such a way that you are able to change the behavior of the program in terms of control transfer. So that's a problem with buffer overflow. So these are the examples of program analysis, that can try to answer these questions. Okay. So the point is, the field of program analysis is an exciting frontier of work. Lots of interesting things are happening, and that continues to evolve because we have ambitious programs, we have advanced architectures, and we have increased expectations. So it's an interesting blend of theory and practice. So what happens in program analysis is we start with intuitions. For example, today in the morning, we started by looking at the intuitions. We said, I am defining I here, and I am computing I plus 4 here, I multiplied by 4 here. Is the value of I changing in between? We try to look at the intuitions, and then we try to make the intuitions more precise. We can formalize it. Then we said, okay, no, I don't have to talk about arbitrary instances of statements. I have to talk about the last occurrence of the previous statement and the first occurrence of the next statement. So we try to make those intuitions more precise, and then we try to formally specify, which is something we will see now. For example, we will see how that common subexpression, global common subexpression elimination that we saw in the morning, how is it formally done. Okay. And then we have to worry about efficient implementation. So you go all the way from intuitions to formal specifications using mathematics, systematic ideas, and then you implement them so that they work efficiently. Okay, provides a much deeper understanding of the programs. It helps us in constructing a variety of abstractions with different views. Okay, there are many intellectually challenging research projects happening all over. I just mentioned this Plateau group. Plateau is the name that we have given to our group at IIT Bombay. It stands for Programming Languages Analysis, Translation and Optimization. So that's our group. It's called Plateau at IIT Bombay. There are lots of interesting projects happening there. So this is an overview of program analysis. We would like to dive into a specific program analysis called live variables analysis. Before I get into it, I would like to pause here and take questions if there are any questions about the general view of program analysis. Does anyone have a question? Because I made many abstract statements, and if there are any observations, if there are any questions that you have, this is the time I can answer those questions. Okay.
Sir,
Yeah.
sir, you told about how we need to cover all the cases of the input program if we are making some optimization. But can we not make approximations for some cases and then have two parts of the program that will run if for some cases some part of the program runs which is optimized, and if we get an edge case, we can run a general program which covers all the cases without optimizations?
That typically happens in dynamic analysis. So what people do is they do JIT compilation, just in time compilation, okay, and they make some assumptions based on the information that they have. So they have an optimized version and they have an unoptimized version, and at runtime they decide, okay, some of my violations, some of my assumptions have been violated, so I cannot use optimized version, I'll go to this version. In fact, one of the things that Professor Manas has done, one of his students is doing, Mitesh, who is coming here as a TA with him for the next week, he has something very interesting. What he does is, in a JIT compilation, he maintains different optimized versions of a procedure. And then intelligently at runtime, he says, okay, I can call this optimized version or that optimized version, or maybe I need to call unoptimized version. So yes, definitely it's possible for us to do that, but that is more relevant in case of a dynamic analysis, because it's a dynamic decision. You can't take this decision statically. So when you combine static and dynamic analysis, yes, it's very much possible and people have done it. And yes, many more interesting things can be done there. Yeah. Okay, any other question? Okay, so let's begin with this analysis called live variables analysis. It helps us identify dead code. We looked at dead code elimination. So that's one of the applications. So we will first do a gentle analysis, a gentle introduction to live variables analysis. We'll continue with this program, but now we will talk about the stack locations. We'll not talk about the heap locations. For the heap locations, we have to do heap liveness analysis, which we will not be able to cover, but let's do liveness analysis of variables x, y, z. This is the program that we are talking about. So we have to first define. So what does liveness analysis do? Liveness analysis tries to ask a question: is this location being used after a certain program point? For each program point, it tries to identify the set of variables whose values are used later. So we will define what is the meaning of use of data. So whenever we read, so let's say we have this data structure, now we are trying to answer this general question which we will use for stack data as well, but use of data means accessing the location and reading its contents. Simply reading its address, simply accessing a location doesn't make the location live. For us to make the location live, we have to access the location and we have to read its contents. So for example, here when we read X, we are reading the address of this object, but this object is not live. What is live is this variable. Only the blue variable is live. If we were to read X dot data, X is live, X dot data is live, because now we are reading the contents of data. If we were to read x dot rptr, x is live and the rptr field of this object is live, this object, this field stores the address of this location, but this location is not live. I'm only accessing the location's address. I am not accessing I'm not reading the contents of the location, right? So now with that, let's try to informally, let's try to intuitively do live variables analysis. We are going to talk about stack locations w, x, y, z, and we are trying to find out which are the locations whose values are required. So at the end of the program, no variable is live. These are all local variables, and I can nullify, I can put garbage value in any location. So the way we try to answer this question, is this location live, is this location useful, is imagine as if we put some garbage value in the location. If we did that, will the rest of the program execution be affected? If it is likely to be affected, then the location is live. If I can guarantee that I can put any garbage value here, but the program execution, the execution of the remaining program will not be affected, then the location is not live, right? Because if the location is red and we put garbage, execution may be affected. But if the location is not red, doesn't matter what value we put, in which case the location is not live. That's the intuition with which we will proceed, and then we will of course formalize it. We'll come up with a mathematical specification of how do we identify that systematically in a program. But for now, let's stay at the level of intuition. So let's go step by step. So here no variable is live at the end of it. So now the scene is this: I have a statement, I know the set of variables that are live here. I try to see what is happening within the statement, and from the set after the statement, I try to infer the set before the statement. From the set of variables that are live after the statement, I try to infer the set of locations, set of variables that are live before the statement. So I have two pieces of information: what locations are live after a statement and what a statement is doing. I combine my intuitions of these two things and I tell what could happen before the statement. So let's use our intuitions. We are given that nothing is live here. Now we have to answer the question, which variables are live here? What is your answer? Which variables are live before statement 8? Is anyone? XYZ are live here. The suggestion is XYZ are live here. How many of you agree with him? How many of you disagree with him? Why do you disagree? Pick up the mic.
After 7, x and y are not actually used, only z is being used.
Yes. Why is X and Y live? Only Z is used. Right? I put in a garbage value, any arbitrary value in X and Y, and the execution of this statement is going to be unaffected. What will affect the execution of this statement? If I put something arbitrary in Z. So therefore, before this statement, only Z is live. Right? So current value of Z is used beyond this program point. It is live, everything else is dead. Right? Now we have made one progress. From here, we have gone here. Now from here, when we go here, what do you think will be live? X and Y will be live. What about Z? X and Y will definitely be live. They appear on the right hand side. What about Z? Will it be live or will it not be live? Need not be live? Okay. Okay. Any other opinions? Z will be live. Why will it be live? Value of Z is changed, then Z is not live. That question was googly. No. That question is googly. Although Z appears on the right hand side, we are not writing into Z. We are writing into the object whose address is held in the Z. Are we changing the contents of Z, or are we changing the contents of the object to which Z points to? We are writing the sum field of the object that Z points to. We are not changing the contents of Z. We are not changing the address contained in Z. In fact, in order to access sum, I have to read Z. So I am reading Z. So Z is live. Right? So here we say X, Y, Z, because if I put any arbitrary garbage value in Z, I will not write this value in the appropriate location of sum. I may end up writing somewhere else. Make sense? Yeah. So here we have X, Y, Z as live. Wonderful. Let's go to the next statement. Before 6, what will be live? Which all variables will be live? X, Y, Z. I am redefining the value of Y. So will Y be live before this? Is the current value in Y required? We need Y because Y is being read on the right hand side. Right hand evaluation of the right hand side happens before we write into left hand side. So if we write some garbage value in Y, we will not get the correct value in Y because this will be wrong. So therefore the liveness set remains X, Y, Z. Right? What will be live here before 5? X and Y. What about Z? So will the variable Z be live here is the question. Z exists. The object pointed to by Z does not exist. Z exists on the stack. The question is Z live or not live? How many of you think Z will be live? Please raise your hands. Okay. How many of you think Z will not be live? And why will Z not be live? No, we cannot access the location of Z. Of course we can. No. I am talking about this statement. Before this statement, okay, answer the question slightly differently. If I put any garbage value in Z here, will the rest of the program be affected? No. Why will it not be affected? Because we are overwriting the value in Z. So if we are overwriting the value in Z, it means that the current value of Z is not required. And if the current value of Z is not required, Z is dead. Z is not live. Something is live if the current value in that variable is likely to be required, but because I am modifying the current value of Z, I don't need the current value of Z, and therefore Z is not live. Right? So we have only X and Y live. Now tell me what will be live here before statement 4? X. What about Y? Y is being overwritten. The current value of Y is not required. So here Y appears on the left hand side and only X is live. Contrast this with this. Here Z appears on the left hand side, here Y appears on the left hand side. But here Z is read on the left hand side. Here y is not red on the left hand side, right? That's the difference. Okay. So for simplicity, assume that nothing is live here. Okay, we'll justify this later. What will be live before 3? X, correct. So now we have X live from here and here. So at this point along either of these paths X is live, and we assume max is some constant, we just ignore that. So X is live and we have X is live. So this is the result of our analysis. First traversal over the program going backward. At each program point we have annotated the variables that are live and the variables that are dead. Okay. However, there is a bit of a problem. Here we are saying X is not live, right? At the exit of statement 3 we say X is not live, but when this back edge is executed, when you go over the loop, from this point onwards, if the execution were to reach here, we see actually X is live, right? Which means that whatever we have concluded in the first traversal is not complete. And why is it not complete? Because we concluded something here before we knew what is here. So in the presence of loops, we have something, this part will influence this, but we have not visited that part yet. And because we have not visited that part yet, it means that we need to redo our computation. We need to find out, some things could change, right? And the only change here would be that X will become live, nothing else changes. So this is the end of iteration 2. So when we are performing program analysis, we are iterating over the program, we are traversing the program. In this case, we are traversing the program in the backward direction, but we will see, as we shall see, there could be analysis which traverses program in the forward direction as well. Something else that we shall see later. There is a certain direction of traversal that we choose, and then we go over the program, and then we go over the program again, and then we go over the program again. We keep going over the program until there is no further change. There are lots of interesting questions. Can this number of going over the program be infinitely many? Or can we guarantee that after a finite number of steps the values will stabilize? Do we know what that finite number of steps is? What is the complexity of this analysis? Does it converge ever? Does it terminate? If it terminates, what is the value on which it converges? All these are interesting theoretical questions which we'll bring out slowly and slowly as we go along. But as you can see, once we have marked X as live here, now if we go over this program again, nothing will change. Can you see that? Going over the program the third time, there is no further change. Can you see that? Can all of you see that? Yes? Okay. Fine. So where do we go from here? So we define, now let's come back to, now we have seen some intuitions, now let's try to define live variables analysis. So we say a variable V is live at a program point P if some path from P to program exit contains an R value occurrence of V which is not preceded by L value occurrence of V. Okay, there are many statements here. The many things being said in this sentence. We'll dissect this sentence. We'll go over one by one. First thing is, we are saying a variable is live at a program point P. We are not saying a variable is live in the program. We are saying variable is live at a point in the program, which means that variable may be live here but may not be live here. It may be live here, may not be live here. So the property that we are discovering, the liveness property of variables that we are discovering depends on the control flow point. This is what is called flow sensitive analysis. The information that we are computing is sensitive to these. We may compute different information for different control flow points. There's some analysis where we do not compute separate information for each control flow point. We'll come to that later. But for now, the first observation is that the information that we are computing, the properties that we are discovering are flow sensitive. They could be different at different program points. This is the first observation. Second, we are saying that if we are computing a set at a program point P, what happens? The discovery of this set depends on what happens after that program. So, we're examining paths starting from P to the program exit. The property that we are discovering does not depend on the start to P, does not depend on the history of execution that reached until P, but depends on the future of the execution from that point onwards, because we want to know whether a variable is used after this point, and therefore we examine paths starting from P to exit and not from start to P. We will see a different analysis which traverses paths from start to exit. And because we are examining paths from P to exit, intuitively that's the reason why we went backwards. Right? That's the second observation. Third observation is we are saying some path from P to exit. So we are not saying every path from P to exit must satisfy this property. We are saying if from P there exists some path in which this value is used, I am fine with it, I will declare it to be live. It may be used along this path, may not be used along this path, that is okay. We will see examples of analysis where we might say this property must hold along every path. Here we are saying only some path, right? So just to summarize, what are the three observations that we have made? The three observations that we have made is, first, this property depends, may vary from one program point to another program point. B, this property depends on path starting at P. Third, this property depends on some path. We do not assert that this must hold along every path. These are the three observations that we have made. Let's come back to the remaining thing. How many of you know what is an R value and an L value? Okay, some of you know, others don't know. So R value is, the name comes from it appearing on the right hand side. L value is something that appears on the left hand side. But more technically, R value means reading of a location. Okay, L value means writing into the location. Now, in the presence of pointers, to objects, this becomes funny, because although here we have Z appearing on the left hand side, it is actually an R value occurrence of Z, not an L value occurrence of Z. Here Y is appearing on the left hand side, this is an L value occurrence of Y. Here we have an L value occurrence of Y, but this is an R value occurrence of Y. For the same variable may have an L value occurrence. So L value occurrence will always have to be on the left hand side, but R value occurrence may be on the left hand side, may be on the right hand side. Right? And the same variable may have both L value occurrence and R value occurrence in the same statement, example being this. We have an R value occurrence of Y, we have an L value occurrence of Y. Right? So with this definition, let's get back to it. So we're saying that at a program point P, starting from P to exit, if there is a path from P to exit in which there is an R value occurrence, meaning in which the value of V is read before being preceded by its definition, it means that the current value in V is useful. Then we declare V to be live. This is a formal definition of an accurate and precise definition of liveness, statically figured out. The reason why this may not be exact is we are talking about all paths, but we don't know whether this path will actually be executed. Maybe there is some condition because of which this path may not be executed, right? So this is an over approximation. We assume that all paths are likely to be executed and we arrive at this, okay? So with this definition of V, let's go to these three examples. In the first example, is V live at P? Yes or no? Yes or no? Apply the definition given there to this example. It is not live. Just use the mic. Again, somebody will complain.
So, like comparing this definition and previously what we discussed, say I'm throwing a garbage value into V, it doesn't matter because V is actually assigned A star B. And again, while you're reading, you read only A star B and not the value which we assigned.
Is she right? Yes? Someone thinks she is not right? Is there someone who thinks she is not right? Yes? Actually, she is wrong. Someone tell me why she is wrong. Yeah?
A equal to V plus 2, V is being used.
Yes. There is another path in which V is being read. So we are talking about liveness of P. We are saying there exists some path in which V is read. In this path V is not read, but in this path V is read. So the gross property at P is that variable V is live. Because if we put garbage value and the program execution were to follow this path, we will get a wrong value in A. Right? So remember, some path notion comes in. Right? What about the second example now? Is it live? No, because there does not exist any path in which it is used before being defined. What about the third example? What about the third example? It is live? Yes. So although it's not used here, it doesn't matter. There exists a path in which it is used. Remember, it's being defined, but before being defined, its value is read. What happens on the right hand side always precedes in the execution compared to what happens on the left hand side, unless in the left hand side we have a read. Yeah. Okay. So this is what we call as a path-based specification. The property of liveness depends on the execution path from here to here. As we shall see later, we will try to come up with a different way of specifying, which is actually not a path-based specification but an edge-based specification. But just observe that we are talking about properties of paths, right? Any questions before I go further? Because it's very important for us to be very clear about this definition. From here on, we will simply try to formalize all these things, try to write mathematics for this. Is okay? Is the concept okay? Fine. Let's proceed. So how do we define data flow analysis for I value variables analysis? So we want to now systematically say how do we discover the set of variables that are live at a program point. So we have these basic blocks. We know in our control flow graph we have these basic blocks and we know what's happening inside the basic blocks. So we have these edges representing control transfers and we associate two sets with each basic block. This is block K, block I, block J, and with each basic block we associate a set called gen, we associate a set called kill. Gen says that this is the set of variables whose liveness is generated by the statements within this particular basic block. Kill is a set of variables whose liveness is killed within this basic block. So these are what we call as local data flow properties. They take into account only what's happening inside a basic block. Right? So we will see how do we define gen and kill precisely as we go along. But gen says if there are sets x, y, z in gen, then we will say liveness of x, y, z is generated within this particular basic block. If we have sets ABC in kill, we will say liveness of ABC is killed within this basic block. So let's assume that we have, now this can be performed independently of what's happening elsewhere. So we can just locally traverse a basic block and compute this set gen and kill using the path-based specification that we have given before. We just look at this. From here to here, is there a use of V which is not preceded by a definition of V? Then V is live. Is there a definition of V somewhere? Then V's liveness has been killed. Right? That's what this says. Okay? So now we also, so this is how we define gen. The set gen n is all those variables V such that V is used in the basic block n and is not preceded by a definition of V. So we are talking about used as in we are talking about R value occurrence. So here x dot sum is R value, x is an R value occurrence, and when we say preceded, the definition is an L value occurrence, and when we say preceded, it's preceded within n. We don't care about what's happening outside of the basic blocks. We're talking about only that particular basic block, right? And how do we define the set kill? We say if variable is modified anywhere, it doesn't matter whether it's read or not. All I want to say is that after this basic block, the value before the basic block is not required. So the liveness of this variable is killed within this basic block. So with this gen and kill, so what does gen mean? Gen says the set of variables with upwards exposed read within n. Okay, the most recent assignments to these variables are useful and they are not dead, and the liveness of this variable is generated in node n. Kill n means set of variables that are defined within n, and the most recent assignments of variables are not useful, they are dead. Okay, the liveness of these variables must be killed. However, there is a bit of catch, we will come to these later. The last point is important. Liveness of these variables cannot propagate from the exit of node to its entry. Okay, so so assume that we know what gen and kill are. Now we define something called in and out. These are the two sets. In K says the set in for the basic block K says that this is a set of variables that are live at the entry of the basic block. Out of K says this is a set of variables that are live at the exit of basic block. Now observe something interesting. We are saying that for a variable to be live, it has to be used along some path. I don't insist it must be used along any path or every path. So therefore I am saying that if something is live here, it should be marked as live here. Similarly, if something is live here, it should be marked as live here, and therefore we can compute out of K as a union of the sets of in J and in K. If I were to insist that this must be live along every path, I would have taken an intersection here. But the union says if something is live here, it will be marked as live here. Something is live here, it will be marked as live here. It may be live in both the sets, that's okay. But my union tells me. So this tells me the set of variables that are live at the exit of the block, assuming that I have the liveness set at the entry of the successor nodes of this basic block. Yeah.
What if our code doesn't visit a part of the block? Let us say it doesn't visit in I at any point of the time during the execution.
During static analysis, we have to assume that all paths are equally likely to be executed. So we are assuming a larger set of paths. So which means that we will cover all executions, we will not miss any executions, but we may have spurious information. We might declare a variable to be live which is not live. It is sound. It's still okay. We will come back to that later. But we are assuming that control flow path represents execution paths. Yeah? Any questions about how we compute out? Okay, now we know which variables are live at the exit of a block. We try to find out the variables that are live at the entry of the block, and that's very easy. I know something is live at the exit of block. If its liveness is killed, then I remove it from out K, because I have reassigned these variables. And If liveness of some variable is generated, I include that at the entry. So at the entry of a block, the set of variables that are live is obtained by removing the variables from out k, the variables whose liveness is killed, and including the variables whose liveness is generated. So when I write in k is equal to gen k union out k minus kill k, that gives me the set of variables that are live at the entry of k. This is exactly how in I would be computed. This is exactly how in j would be computed. So given something at the exit of a block, we know how to compute what happens at the entry of the block. And then we just repeat it. We just repeat it for every node in the block. That's all that is required in order to compute live variables analysis. Before I go further, I want to pause here and make sure that all of us are on the same page about why out k has been written like this and why in k has been written like this. If you have a question, this is the time to ask. Is it clear? Is it obvious? Okay, so let us proceed. Why is out k written like this? Would someone like to explain to him? Just want to see if someone has an answer. His question is, why is out k written like this? Would someone like to answer that question? Anyone would like to make an attempt at answering that question? You don't have too many friends here, is it? No one wants to answer your question? Please tell me, why have we written out k like this? I want you to speak up. Don't remain silent. I want you to ask questions. I want you to make observations. I want you to answer questions. Don't remain passive. Yeah.
So we are analyzing like what is live in our block K. But to do that, we are also going in the different blocks after K is going. So those
Yes.
blocks are I and J.
Yes.
So we are analyzing the liveness of variables, like this is happening recursively.
Yes.
So like in those blocks, we are analyzing the liveness.
Yes. So we have liveness of in I and in j. We have this set.
Yeah.
The question is, why is out k defined this way? That's the question.
So out case, we are trying to just take a guess at what is live after this block is happened.
Yes.
And we are not outright directly including that in the liveness of our particular block, because if our block is killing some variables, like we are reassigning their values, so we are subtracting that set from this out k. So that gives us the exact addition that we need to do to our live variables.
Yeah. So the last thing that he said was about in k. The reason why we define out k is, I want to include in out k every variable which may be live anywhere in any successor. So therefore, simply taking a union of in of the successors gives us the set out k, because we are saying any path is good enough. That's the reason why we take a union, right? So we are saying, if variable x is live here, I want to include it in out. If it is live here, I want to include it in out, and therefore taking a union over all successors gives me that information. Okay, so much so for pictures. So these are global data flow properties, and this is what is called edge based specification. Remember, we are computing liveness of this by looking at just one edge in the path. We are not looking at the entire path. We are assuming that the effect of the rest of the path has been accounted for in this n, in j. So therefore we have edge based specification. We defined our property as the property of a path. Now we are inductively computing it as a property of an edge, and we are saying composing the effects of all edges will give us the property of paths. Very interesting theoretical question. Do these specifications coincide? Turns out that for live variables they do, but for some analyses such as constant propagation, they don't. And if we have time, we'll look at the reason why that is the case. Okay, so much so for pictures. This is how we define live variables analysis. I have written just what we have written here. I've just written that in a mathematical form. So what I'm saying is, at the exit of a node, what is live is a union of in of all the successors, and if it happens to be end block, then it doesn't have any successors. So we are assuming that our control flow graph has this unique property that it has distinguished start nodes and distinguished end nodes. Start node doesn't have an incoming edge and end node doesn't have an outgoing edge. We always set up our basic block like that, and that's the reason yesterday some of you asked, made an observation, why is there a unique return statement, why is it a separate basic block? This is the reason why end statement is separately identifiable. Okay, so we don't want any edge out of the exit block, and therefore we can safely assume that the liveness at the end block is given as BI. BI stands for boundary information. Okay, so here in and out n are sets of variables, and BI, boundary information, tells us this is the effect of what's happening within the caller. I have at the end of a procedure which variables are live depends on whether a variable is used in the caller. So if we restrict ourselves to local variables, which is what we will do now, in that case this BI becomes empty. So at the exit of a program, at the exit of a procedure, no local variable is live. For global variables, we have to do something. That's a part of interprocedural analysis, which we will not be able to cover. So for local variables, we will assume phi, no variable is live at the end of the procedure. So this is how we write the equations. These are called data flow equations. This is how we write the data flow equations for computing liveness of variables. Before I proceed, once again I would like to stop here and take questions. Does this make sense? So you are going from intuitions, we are trying to formalize, make the intuitions more precise, and then we are trying to make a mathematical statement for that intuition, right? So we have this equation. Does this structure of equation resemble anything that you have read before? Have you studied such equations before? Let me give you an answer. Yes, you have studied, and you have to tell me when you have studied. This is just a system of linear simultaneous equations. Earlier you have solved equations like x is equal to y plus something, y is equal to x star something, and then you solve it, right? So you have done that. This is just a system of linear simultaneous equations, except that here when these variables are not integers or real numbers, but these variables are sets, right? Okay, so let's look at how we expand this to our program. So we say in n, at the entry of n, whatever is out, whatever is live at the exit, from that we remove whatever is live at the entry, and then we add whatever is live, whatever whose liveness is generated. So we have this set of equations. The interesting thing to observe is the following. Okay, we have a loop here in the program, and we are defining into using out to. We are defining the value at in of 2 using out of 2. You can see it. We have out of 2 appearing on the right hand side, that is defining in of 2. Now out of 2, 2 is this block, I am sorry, not this block. In of 2 is defined in terms of out of 2. Okay, out of 2 in turn is defined in terms of in of 3. So we have this propagation happening. In of 3 defines out of 2, out of 2 defines in of 3. How do we get out of 3? Out of 3 in turn depends of in of 2, which means that there is a cyclic dependence. In of 2 depends on itself because of the presence of the loop. Out of 2 depends on itself because of the presence of the loop. In of 3 depends on itself because of the presence of the loop. Out of 3 depends on itself because of the presence of the loop. So what that means is, when we start computing in this direction, here we know out 8 is empty, I can substitute out 8, I know what is kill and gen for basic block 8, I can compute in of 8, and then that will not change in the next week visit. But when we reach here, we don't know anything about in of 2. So we have to assume something. We assume initial value. And in this case, initial conservative value is an empty set. So we proceed with an empty set. We proceed like this, we compute, and then we get some set at in. We have to substitute it here and once again recompute this part. We have to keep recomputing, we have to keep refining these sets until these sets converge, right? There is a cyclic dependency, right? Okay, so let us proceed. So let's do live variables analysis for this example. Once again, we have gen and kill computed. Here liveness of z is generated, liveness of nothing is killed. Here liveness of x, y, z is generated in this statement. No liveness of no variable is killed. Here liveness of y is generated and liveness of y is killed. This is an interesting thing. Within the same block, liveness of y is generated and liveness of y is killed. The meaning of liveness of y is killed is that if y is live here, it's not because it was live after the statement, it was because this liveness was generated within the statement. So gen and kill sets need not be mutually exclusive. Gen and kill sets may have an overlap between them, right? They may be intersecting. Okay, here liveness of nothing is generated, however liveness of z is being killed. In this statement, liveness of x is generated, liveness of y is killed. Yeah, before being defined. Yes, yes, because we are reading the value of z in this statement and not defining the value of z. This is an L value occurrence of z. Sorry, R value occurrence of z, not L value. So if I am reading the value of a variable before being defined, we'll mark it as live, right? What I am trying to say is, in this block, which are the variables whose value, in this statement, which are the variables whose values are read before being defined? Why? Z we are reading, because we are writing into the sum field of z, we are not writing into z. So let me show it pictorially. So what this does is, what we are trying to say is, we have this variable z on the stack and we have an object in the heap which has this field called sum, into which the value is being stored, right? So I can't store a value here until I read this. This reading of this gives me the address of this object. So z dot sum is equal to something, meaning I am writing into this object and therefore liveness of z is generated. If I write something, let's say I change Z. So instead of, maybe I write some value, garbage value, and Z starts pointing here. So instead of the value being stored here, it will be stored here, which is not what we want. So therefore Z is live here. It's an R value occurrence of Z. Right? Okay. So here in this statement, we have liveness of X generated, liveness of X being killed. Right? Here we have liveness of X being generated, and in the first statement, liveness of X is generated and the liveness of Z is being killed. Now I can perform the computation. Here I said gen and kill need not be mutually exclusive. Here Z is an R value occurrence, and I initialize everything with empty set, and now I start computing. So if I were to go backwards, I would compute this as liveness information. Here, because liveness of XYZ is generated, I have XYZ live here, XYZ live here, XYZ live here, XYZ live here. Now liveness of Z is being killed, so it's removed. We have XY live here, we have XY live here, we have only X live here because liveness of Y is being killed. Right? So this is our first iteration in which we compute. Now observe here that we have to compute the out of this from the in of its successors, and at the in of this node X is live, but here out is empty. So when we recompute, we will get this value X being live here. In the second iteration, we get these values. There is no change here. Here we get X is live, X is live here as well. Earlier also X was live here. So the only change here is at the exit of this node. Now if I were to recompute, as you can see, nothing will change. Right? Does it make sense? Yes or no? Right? Okay. So let us proceed. So we can create larger basic blocks as well. Here we have taken a single statement basic block, but we can create basic blocks like this. In this basic block, we have only X in the gen set and we have YZ in the kill set. Why don't we have, we are reading X here, so therefore we have X here. We are also reading Z here, so why are we saying Z is being killed? Why are we saying Z is not in the set gen? Yeah, any guesses? What is the definition of liveness? The definition of liveness is a value as is read before being defined. I am reading Z, but within this block it's defined before it's being read. So the value of Z that's coming from here is not being read, and therefore Z is not in the set gen. Right? However, the value of X is read, and it is this value of X that's coming from here, therefore it is read. So this is gen and this is kill. Is it okay? Does it make sense? I have to give you many problems to work out. I can see that all of you are confused about this, but we will do tutorial problems to solve this. Okay. Now the main point that I want to make is, we have gen and kill, we compute in and out, we effectively get the same result. Okay. So let me just ignore these slides. Let's come to the tutorial problems. These are matters of detail. So let's first look at where is it being used. It's used for local register allocation. A variable X is live in a basic block B, then it's a potential candidate for register allocation. I would like to keep it in a register. It's also used for dead code elimination. So if I have an assignment X equal to something and X is not live after this assignment, then the assignment is dead. I am writing into a variable that is not read. So this is dead code elimination. Right? Okay, here is a tutorial problem. Please compute in and out of this basic block. I have given the gen and kill properties. Please understand gen and kill properties and compute in and out of for this particular programs. Your TAs will help you. Lunch is available to those who solve this completely. Others will get lunch after they have solved this, not before. So the way I would like you to solve this is the following. Let me give you a structure in which a format in which you should write your answers. So you can create a table like this. Node 1, 2, 3, 4, 5 and 6. And then you can say, so this is node n, in of n and out of n. This is iteration 1, and then if required, iteration 2, in of n, out of n, and if required, iteration 3, as I said yesterday, we had abstract stories, today we have concrete stories. Nisha and Ramya, you randomly peep into the notebooks of the people. Uh-huh. Okay, yeah, good point. Yeah, Nisha is right. Okay, so this is a format. Let me write the equation here. You will need the equation. Yeah, okay. Okay, can't clean the board anymore. I am saying in of n is equal to gen n union out n minus kill n, and out n is equal to empty set or union of p s in successors of n in of s if n is end otherwise. This is the equation that you should be using. The first thing that you should do is just make sure that you understand in and out n, the gen and kill. Okay, initialization has been given as empty set everywhere. Now you have to understand why is it that gen is empty and kill is abcm. You have to answer that question to yourself. These slides are, by the way, available on the Google Drive. So if you want, you can look at these slides, download them from the Google Drive and look at them uh, in your laptop. Try to compute beginning with block 6. Don't begin with block 1. We'll come to that question later. What happens if we begin with block 1? But for now, let's just make sure that you're able to compute this. See, doesn't have a notebook. Do it on notebook. Make a table like that. Oh, I wrote before. Make a table and then you'll be able to write. Show me what you have written. 6 is empty. This is empty. That's right. This is empty. A, B, C. That's right. For 4, yes, yes. For 3, you assume nothing. So A is live. Oh, this is out first, is it? No, then you're confusing. Why is A live at the out of 3? No, but we're doing the first iteration. We have to do iteration by iteration. Don't write the final solution. You have to just give me what is there in the first iteration. Right? First time you visit node 3, do you know that A is live at the out of 3? You don't, because you have not visited 2 yet, right? So in the first iteration, when you try to compute this, its value, because this value has been initialized to empty set, this will remain empty. Remember, initial value at each program point is empty set. So please correct it. Feel free to discuss with each other. No, maybe you should form pairs and discuss with each other and do it. Talk to your neighbor. It's a good idea. Shall we make groups of 3 each and each group should solve it? Please decide, please move somewhere, sit with 3. I want to see 3 people discussing together. Here we have 3, maybe someone else should come here, shift here. Please form groups of 3 each and solve it. Please move somewhere, please someone please come here. Yeah, one of you can come here. There are 2 there. One of you can come here. Please sit here. Come here. Please come here. One of you come here. I want to see groups of 3 each. Yeah, you 4 of you, please make groups of 3 each. Please shift somewhere else. Yeah, one of you can come here. Please come here. All are friends. Don't worry. Yeah, come. One of you come here. Yeah, I want to see 3 people. No, please. Yeah, please make groups of 3 each. Come on, quick. One of you move out from there. Please discuss with each other. Please form groups of 3. Discuss with each other. Yeah, maybe. Yeah, one of you come here. Yeah. Form group with anyone. I don't care. Or you ask someone to join you. Yeah. Please. Maybe in the middle, one of you can shift here, so there are groups of 3 each. Yeah. Yes. Because that's the value that's modified. We, if we read a variable on left hand side, we don't kill that. But here, there is no such case. We kill it because we are overwriting it anyway. So the current value is not required. Yeah. Please discuss with each other. Discuss with each other. Ask those questions. Mhm. No. No. Please discuss with each other freely. I don't mind if it becomes a fish market, but please do discuss. So next 10 minutes are very, very important, because next 10 minutes will decide which group gets lunch and which group doesn't. So one group has already done. Which other group has done it? Please raise your hands. No other group has done? Uh-huh. So I think everybody is confused about how to compute out of 3. Remember, in order to compute out of 3, you're going to pick up the value of n of 2. When you reach here first, the value of in of 2 is empty as given here, right? So all you have to do is to pick up the latest value in the in and out of successors. That latest value could come from a previous iteration or would come from the same iteration, it does not matter, right? Okay. uh, why is T1 in kill? Why is T1 in kill of 5? Because it is being defined. Why is T1 not in gen of 5? Because although it is being read, this read is preceded by a write, whereas there is a read of C which is not preceded by a write of C. So those of you who have finished, think of what would happen if we were to go in the order 1, 2, 3, 4, 5, 6 instead of 6, 5, 4, 3, 2, 1. Please think about it. So we will split for lunch, but the fun will continue after lunch. So let's split for lunch, but I want you to solve these and many more problems. Okay. So let us leave for lunch now because the mess will close otherwise.